write them down here so that one can see them. Let E be a vector bundle of rank n and degree d on C. C is a smooth projective curve of genus G greater or equal to 6, greater or equal to 2. I don't write it down again. Then we define gamma, the invariant gamma of E, to be 1 over n times the degree d minus 2 times h0 of E minus n. Right? And the invariant gamma n, which is an invariant of C, of course, which is the minimum over all vector bundles E, over all numbers gamma of E, where E is semi-stable. That's okay. Semi-stable of rank n. And h0 of E is greater or equal to n plus 1. And the slope of E is lesser equal to G minus 1. We defined another invariant, gamma n prime, which is gamma n prime of C, to be the minimum over all vector bundles E. Again, same here. E also semi-stable of rank n. But now the difference is that it has more sections, at least if n is greater or equal to 3, and the slope is also lesser equal to G minus 1. If n is equal to 1, both were the usual Clifford indices of the curve. And moreover, we defined the gonality sequence. So gonality, so let's call this the rth gonality of the curve R, is a number. So dr to be equal to the minimum over all degrees of line bundles. So L is in peak, L in peak of C, right? With H0 of L greater equal to R plus 1. So for R equal 1, this was the usual gonality. For R equal 2, this is the minimum of all degrees of curves in P2, maps of degrees of maps of curves into P2, and then we saw that often one has dr over R greater or equal to dr plus 1 over R plus 1 for all R, or for some R. Doesn't matter for all R. This is often the case, very often. For example, for a general curve always, and for several other hyperelliptic curves and trigonal curves and quadrigonal curves, this is always the case. In some, we had only one counterexample. That's fine. Okay, this definitions I'll use now and write down the first. And I would like to, my main aim is to see how one uses these variants here, for which are for linear systems, and how one uses them for vector bundles. So let me, fourth section now, first results. So theorem 1, I write down now 2 theorems and 2 corollaries, and afterwards, I mean the proofs are quite involved. But afterwards, I will point out the main ingredients of the proof, and you will see how these come in, these invariants. Okay. So E semi-stable vector bundle of rank n and degree dn. Dn is this number here for n, right? The nth tonality. So they are quite special degrees, but anyway, in this case, we can say something. Then we have that if dp over p is greater or equal to dp plus 1 over p plus 1 for all p less than n, which is often the case, but I mean not always, and we don't know, since we don't know for all curves these invariants, we have to assume it, right? And if dn is different from n d1, well, if it's equal here, we have this theorem of Eisenbart saying, well, how this came in, so if this is different from it, then we have that h0 of E is less or equal to n plus 1, and actually this equality here can be attained. So we know, in this case, a specific upper bound which is sharp, and exists a semi-stable, abbreviate is semi-stable bundle with h0 equal to n plus 1. So in this case, the bound is really sharp. That's what we want to have, and then for other degrees we will build this up and get some consequences. Okay. Second, we have also a result if this is equal, right? And then if dn is equal to n d1, then actually h0 of E is less or equal to 2n, and moreover also here the equality can be attained. And there exists a semi-stable bundle with h0 equal to 2n. So in these cases the inequalities are sharp, and this is actually what one wants to have for all degrees, not only for the degree dn, of course, right? So a corollary, if again dp over p is greater or equal to dp plus 1 over p plus 1 for all p less than n, and E is semi-stable of rank n and degree d lesser equal to dn, then actually Merca's conjecture holds. Then we can say that Merca's conjecture holds. This is not an immediate consequence of this, but it is a corollary. One has to work a little bit, and I don't give the details of these proofs. Here I give some. Just in a minute I will give some the main ingredients, but the details it's quite involved and long. But with these ingredients you can prove this, actually, right? And also this here. So using this we prove theorem 2. Again using this here. If C is a curve with Clifford index, usual Clifford index greater or equal to 2. Usual Clifford index here. Then we can compute some of these invariants, higher Clifford indices. If n is greater or equal to g, then we get gamma n is equal to 1 plus g minus 2 over n. Second, if n is equal to g minus 1, then we get that gamma n is equal to 2 plus 2 over g minus 1. C, if n is equal to g minus 2, then we get gamma n is equal to 2 plus 1 over g minus 2. And D, if n is equal to g minus 3, we get that gamma n is equal to 2. Right? For n equal to g minus 4 or smaller, we do not get anything like that. I mean, this is the method of proof stops here. But anyway, we get these results, and it's difficult to find a pattern even, to make a conjecture or something, right? Somewhat, I don't see a pattern. Right, how this could go on, for example. I don't know. Okay, anyway, as a corollary, immediate, not immediate, but I'll write it down. As a corollary, we get, first thing, that if gamma 1 is equal to 0 or 1, then, well, this is not a corollary here because this is sort of immediate, but I also write it down here. Gamma n is equal to gamma n prime is equal to gamma 1 for all n. So for this small values of gamma 1, everything is clear, right? But this is a corollary here. If gamma 1 is equal to 2, then we get gamma n is equal to 2 for all n also lesser equal to g minus 3. For greater equal to g minus 3, we have these numbers. Okay. These are the first results. I mean, you see that in the results these inequalities come in. And I would like to point out how they come in. Right? There are actually two reasons how they come in. So I give the main ingredients of the proof here. Of the proofs here. These, I mean, you can maybe forget about the results here. They are perhaps not so important. I don't know.
Excuse me. So do you already have some case where gamma n is different from gamma 1?
Oh yes. In particular. Yeah, clear, because I mean gamma 1 gamma 1 depends on the curve, but this was for all curves, right? But if maybe I should have shown if n is 1, then this doesn't say very much, right? Okay. So yeah, the main ingredients of the proof are first of all the little lemma of Paranjape and Ramanan in their paper on Green's conjecture. It's a very little lemma, and I'll prove it, but it turns to be really crucial for us. So, what is the lemma of the first ingredient? Lemma of Paranjape and Ramanan. They have a paper on Green's conjecture in which this also plays a role. This is the following. If E is a vector bundle of rank n with, well, we do not, I do not write down the original formulation of this lemma, but our formulation, where these, in terms of these DRs, right? One can express this in terms of these Carnality invariants. They expressed it a different way. But anyway, it's the same lemma. With H0 of E greater or equal to n plus s, with s for some s greater or equal to 1. For some s greater or equal to 1. Right? Then, suppose E has no proper subbundle n with H0 of n greater than the rank of n. With H0 of n greater than the rank of n, or greater or equal to the rank of n plus 1. Okay? Then the statement is that the degree of E, which is the degree of the determinant line bundle, right, is greater or equal to dns, n times s. Right? Let me prove this. The proof is very simple, so I give the simple proofs here and leave out the more complicated ones. Right? The proof is very simple but very interesting. Well, it's by contradiction. Suppose H0 of det E, suppose H0 of det E is lesser equal to ns. No, but if you what do you have to show? Well, I will see later. I'll just start with this. Suppose this is the case. We get a contradiction. So then we get that this is greater or equal to, and then we get what we want. Okay? So then we consider the map. So assume this. Consider the map, canonical map of the nth wedge product of H0 of E So this is a vector space. We take the nth wedge product, and there's a map into the H0 of det E. Canonical map, because this is the nth wedge product here. The map is just you take S1, wedge, 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 Sn, and map it to S1, wedge, 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 Sn, right? Consider this just as a, I mean, the determinant is just wedge. Determinant E is just wedge Ne. Right? This is a canonical map, wedging the sections. Consider this map. Then one has also always here a cone of decomposable vectors. In every vector space, if you take a wedge product, we have a cone of the decomposable vectors. I write down what it is. Form a cone. So the cone of decomposable vectors S1 wedge Sn. I mean the elements of the wedge product of the nth wedge product of a vector space are sums of decomposable or linear combinations of decomposable vectors, right? And the decomposable vectors here, they span a cone, and one knows explicitly the dimension. I mean, this is easy to work out, and this is of dimension greater than greater than ns, actually, right? This is easy to work out. I mean, by this assumption, is of dimension greater. Not by this assumption, but this is always of dimension greater or equal to ns. Let me write down here, greater than ns. Okay. Okay. This means, what does it mean? There is a decomposable vector here which goes to 0 here, right? Which goes to 0 here. Okay, so exists decomposable vector which goes to 0 under this map. Right? And what does this mean? I mean a decomposable vector different from 0, I should write different from 0, which goes to 0 here. If you have a decomposable vector different from 0, this means that the sections are linearly independent, right? If the sections are linearly independent, they generate a subbundle. They generate a subbundle of smaller rank because, I mean, this E cannot be generated by n sections, so this means exists a subbundle n with H0 of n greater than the rank of n, because this subbundle has rank smaller than n. But H0, these are all sections of this subbundle, so it has at least n sections. So with this property, this is a contradicts our assumption. Suppose it has no subbundle with H0 of n greater than n. This is a contradiction. Okay, and this assumption was wrong, so we get that H0 of det E is greater or equal to ns plus 1. And now look at the definition of these gonality invariant. Right? So this means that that the degree of that E by definition, so by definition of dns, this means that H0, that the degree of the determinant of E, this line bundle, is greater or equal to dns, because dns was the minimum number, such that H0 of a line bundle has so many sections, right? So the degree of this is greater or equal to dns, but the degree of the determinant is the degree of E. Okay? This is very interesting and important lemma. And I mean, this idea here, really, to use this map here, this is due to Paranjap and Raman. I mean, this is a very clever idea, I think. Right? Okay. So this how it comes in. First of all, we'll see later how how this lemma is used for our proofs. Okay. So the next ingredient is the dual span construction, which actually was used already in Pete's talk of Wednesday, but which is very important. Dual span construction. Suppose, well, I give it only in a special case again. Suppose L is a line bundle which computes Dn. L computes Dn, which means that the minimum is taken here, and we saw then L is actually H0 of L is equal to R plus 1, and we saw also that it's generated by its section. Okay, so by property 2 of yesterday, we saw, because since it computes Dn, that L is generated, meaning generated by its global sections, and moreover, H0 of L is equal to R plus 1. Right? This was one of the elementary properties. And then, the dual span construction always works if a line bundle is generated by its sections. So we do this now, and this then define EL by the following exact sequence. Actually, we define EL dual. Right? This is defined as the kernel of the map. Actually, this map on Wednesday was called ML, right? So this turns up many times in algebraic geometry by several people. And it has been proven many times for many cases that this is a semi-stable or even stable bundle. I mean, the proofs, there are proofs by Paranjapal Ramanan, they proved it in one case, and by Kempf, by Green and Lazarsfeld, or Lazarsfeld alone, I don't remember, and Butler. Butler also defined the notion dual span. Dual because he takes the dual here, right? The dual span construction. And we'll add another case, theorem. If dp over p greater or equal to dn over n for all p less than n, this is actually weaker than this condition here, right? Weaker than this condition in general. But anyway, then EL is semi-stable. And second, if dp over p is greater, here we have greater equal to dn over n, which is also often the case for all p less than n, then EL is even stable. Right, so there's one more theorem where this bundle is stable or semi-stable, right? I mean, if EL is stable if and only if the dual is stable, so that I could also have said EL dual is stable, but for us EL will be the important thing. Okay. So let's prove this again in order to see how these inequalities come in, right? Okay, so what do we have to show? EL, I only want to show that it is semi-stable and stable is the same proof, the same argument. EL in M be a quotient bundle of rank P less than N. The definition which I gave for semi-stability or stability was in terms of subbundles. Of course, you can do this also for quotient bundles, right? Then the inequalities get the different. So what do we have to show? We have to show that mu is actually greater or equal to mu of EL. For subbundles, the definition was if you have a subbundle, then the slope is lesser equal to the slope of the bundle, and for quotient bundles, the opposite inequality. Okay. So now, EL is generated by its sections. This you see by just dualizing the sequence. If you dualize the sequence, you get L star, vector space, here trivial bundle, EL. So you see that this dual sequence is surjective, so EL is is generated by the sections. Now, I write, EL is generated, and H0 of EL is equal to 0, of EL star is equal to 0, because on the H0 level, this is an isomorphism. Then this has to be 0, the H0, right? Okay, this means, if EL is generated, then also every quotient is generated. So this is generated. So this implies M is generated. And if you dualize this sequence, this goes into M star goes into EL star, which means that also M star has no sections, okay? And M star, H0 of M star is 0. Okay? So now there's the theorem of Sour. If a vector bundle, any vector bundle on any variety is generated by its sections, then there is it of rank P, then there is a P plus one-dimensional subvector space on a curve. We are on a curve here, which generates already. So already P plus one sections generate. This is a lemma of Sour, which is written in the classical paper of Atiyah on vector bundles on elliptic curves of 1970, for 57 or something. Right? So by a lemma of Sour we can choose a P plus one dimensional subvector space, subspace, V in H0 of M, which generates M. Okay, this we do and have an exact sequence. Maybe I can write out, although we need it later, but I will recall it then. So we get an exact sequence. So V tensor OC goes to M, goes to 0, right? What's the kernel? Well, this is of rank P plus 1, this is of rank P. So the kernel is a line bundle. Comparing determinants, we get just that this is det M star. Okay? Now we dualize this sequence. We get M star. We get actually, the dual vector space here, V star, tensor OC, det M, 0. Okay? This means, what does it mean? Well, M star, H0 of M star is 0, so H0 of this is a trivial bundle, is P plus 1, so this means that M, H0 of that M is greater or equal to P plus 1. Okay? To P plus 1. Okay, now we again look at the definition of D. Yeah, this means by definition of dP, so by definition of dP we get the degree of M, which is the degree of the determinant of M, okay, is greater or equal to dP. Right? The invariant, the P's gonality invariant dP, because this was the minimum of all those line bundles for which the degree H0 is greater or equal to P plus 1. So we get that this is greater or equal to dP. Okay? And now we look at, with this we can just prove the inequality. What was, now we get mu of M. this was by definition degree of m over p. Degree of m over rank of m, and rank of m was p. Okay? Yeah, this is, now we see degree of m is greater or equal to dp. So we get that this is greater or equal to dp over p. Right, and now we use our assumption. I mean, you see how for vector bundles this comes in not only in the lemma of Ramanan, but also by the definition of semi-stability. We know yet that this is greater or equal to dn over n. Okay, and dn was just the degree of E over rank of E over n, which is the slope of E. Let me write down, this is just slope of E. Okay, so we get what we want. This mu of m is greater or equal to mu of E. So this is the proof. And you see, if you have the strict inequality here, you have strict inequality here, and you show that it's stable. I mean, this is the proof, right? Very simple in this case. Okay. Yeah. So this was, I mean, with these two lemmas or theorems, I don't know, we proved all the theorems, but I mean, they are more, the proofs are more intricate. You have to use this several times and for several ranks, etc., etc. Okay, these are the first results. The second series of results which we have concern the comparison between the invariants gamma n and gamma n prime. So, section 5, relations between gamma n and gamma n prime. We have relations for this for gamma 2, gamma rank 2, rank 3, rank 4, rank 5, and then it gets more and more complicated. The easiest case is the rank 2, and I will give the proof of rank 2 completely, and then the others are just more complicated but using the same ideas. Right? So, and again you will see how these lemmas are used. So, theorem 1 is for rank 2. Gamma 2 is actually equal to the minimum of gamma 2 prime and d2 minus 2 over 2 minus 1. So if we have gamma 2 prime, we have also gamma 2, right? But not conversely, unfortunately. Okay, so what do we have to show? Let me give the complete proof of this. To show, what do we have to show? We have to show that gamma 2 is greater or equal to minimum gamma 2 prime and d2 over 2 minus 1. Why? Because, no, maybe I call this statement star, and then later we will prove star, but first I will give a reason why this is. Because gamma 2 is, of course, less or equal to gamma 2 prime, because here we take the minimum. Here we take the minimum over degree over this gamma of E for much more, perhaps much more vector bundles, right? This is a less restriction than this one. So this is by definition. By definition. We have also to show that gamma 2, well then it's, yeah. Moreover, we have to show moreover the equality gamma of E equal to d2 over 2 minus 1 can be attained. I mean, there is a semi-stable vector bundle, so exists in E semi-stable such that with these properties. That's enough. Then we know already that gamma 2 is greater or equal to the minimum here. I mean, greater or equal to this number. Okay? To see this, we use this theorem here. Actually, let me, I'll leave this theorem and then make the proof here. Okay, so let L compute D2. That means that L is a line bundle such that H0 is greater or equal to 3 with this equality, i.e. degree L equal to D2, and H0 of L is actually equal to 3. If it computes, we saw that it's actually equal to 2 plus 1, which is 3. Okay? Then EL is semi-stable by theorem 1 here. We have to check this one here, but if we have 2 here, we have to check this only for D1, and this is always the case. D1 over 1 is always greater or equal to D2 over 2. That one can see easy. Okay? So this is semi-stable. And what's the degree of EL? This was D2. This was by the construction here, the degree of L. It's the degree of EL, right? Because the degree of L is minus the degree of this one here, and the degree of the dual is again minus, so this is degree of L is D2. And moreover, we have H0 of EL. What is this? H0 of EL is 3. Is equal to 3. You dualize this exact sequence and you see that it's 3, which is equal to 3. Okay? Maybe greater or equal to 3. By construction. 3 or greater or equal to 3. Maybe greater. So we get gamma of EL, which is by definition 1, 2 minus 2 times 3 minus 1, which is greater or equal to D, which is equal to, this is greater or equal to, this is greater or equal to D2. If you work this out, this is D2 over 2 minus 1. D2 over 2 minus 1. So minus, let's see, 3 over 1 minus 1 is minus 1. Why minus 1? Minus 1, and I... Why is it minus 1? 2 times 2 is 4, D2 over 2 minus. Simple mistake.
This is minus 2.
Fun?
Minus 2.
Minus 2, yeah, this is just an error here, minus 2 by definition, yeah. Okay, well, there was here. Okay, of course, minus 2, and then it's 1. Okay, this is just a. If you have this during the talk, you get, of course, confused. So we only have. So this is what we want to show here. So that we only have to show this statement. Okay. So now the proof of the statement, and this was sort of the element here in the box. So let's prove the statement. This is a more difficult thing. Okay. Yeah. Proof of star. Suppose E is semi-stable of rank 2 and degree D, and with H0 of L, H0 of E greater or equal to 3, right? Which is n plus 1 in this case. Equal n plus 1. N is 3. N is 2. N plus 1. Okay? What do we have to show? I mean, this means suppose E contributes to this Clifford index, gamma n. Okay? What we have to show is gamma of E is greater or equal to minimum of gamma 2 prime and d2 over 2 minus 1. That we have to show. Okay, then we are finished. Okay, so this I used already, so I don't need it anymore. Used in the argument there. So, if h0 of E is greater or equal to 4, then it contributes to gamma n prime, right? So by definition of gamma n prime, we know that gamma of E is greater or equal to gamma n prime, okay? So which is actually equal to 2n, right? So we get that gamma of E is greater or equal to gamma 2 prime, which is greater or equal to the minimum. So, this is what you want. So let's write this greater or equal to min. Gamma 2 prime, and then the other one was what? d2 over 2 minus 1. So we are finished. So suppose h0 of E, which was by assumption greater or equal to 3, is equal to 3. Okay? Then, if degree of E is greater or equal to d2, then, well, gamma of E, I can write down what gamma of E is, actually greater or equal now. So this is greater or equal to 1. Well, then we have here D, which is now greater or equal to d2, minus 2 times, and again, h0 is equal to 3, minus rank is 2. So again we get this is d2 over 2 minus 1, what we want. Okay? So in this case we are already finished. So suppose degree E is less than d2. So suppose degree E is less than d2. Then we use the lemma of Ramanan. So I write down PR lemma. Maybe I write it down again because it's not somewhat, yeah. I write down in this case E of rank 2 with h0 of E equal to 2 plus S. And S in our case is 1. S equal to 1. Right? I just write the lemma here. It was an S here. If E has no subbundle, no line, well, now a proper subbundle of a rank 2 vector bundle is a line subbundle. Okay, no line subbundle. N with h0 of n greater or equal to the rank of n plus 1, which is actually now 2 here. We had here greater than rank, and this is the same here, right? Which is now equal to 2. Then the statement was degree E is greater or equal to dns, was the statement. Now n is 2 and s is 1, so this is d2. So again we get degree E is greater or equal to 2. And we can, degree E is greater or equal to d2. And we can assume that we have the same inequality here. Okay? So then we are finished by the lemma of Paranjpe and Ramanan. Okay? Now in the other case, what's in the other case? So maybe I write it here. So let n be a subbundle. So let n in E be a line subbundle. With h0 of n greater or equal to 2. This was just the assumption that there doesn't exist such a line subbundle, and now we assume there exists one. Okay? Then we have degree n over 1. The slope of n, I mean, is the degree by the rank, and the rank is 1. And this is, of course, now, since h0 of n is greater or equal to 2, this is d1, greater or equal to d1 over 1. by definition of D1, okay? And now we use the assumption. By assumption, this is greater or equal to D2 over 2. Here you see the assumption and how these gonality invariants come in here, right? D2 over 2, and this is greater or equal to degree E over 2, which is the slope, right? So we show exactly that this is a contradiction to the semi-stability of E. Right? This contradicts the semi-stability of E. Contradiction to semi-stability of E. So you see another, this invariance here these gonality invariants came in on the one hand side by Paranjapa-Ramanan lemma, but also by the definition of semi-stability. So you see that these invariants for linear systems of line bundles are very important for the vector bundle case. Okay, so now I state maybe the other theorems. This, the same proof works for gamma 3, gamma 4, and gamma 5, but it gets more and more complicated. Here we have a line subbundle. If you are in rank 3, we could have a rank 2 subbundle. If you have a rank 4, we could have a rank 3 subbundle, and a rank 2 subbundle, and a line subbundle, so everything gets more complicated. But the proof is the same, right? Only it's longer. The same ideas, just Paranjapa-Ramanan lemma and the semi-stability, these inequalities. Okay, so let me get just the results. So for rank 3, theorem 2, rank 3 and rank 4, suppose D2 over 2 greater or equal to D3 over 3, then we have gamma 3 is equal to the minimum of gamma 3 prime and 1/3 D3 minus 2. Right? So this we could write also as 1/2 2 minus 2. So at this point we thought there is a pattern. Maybe we can prove a general theorem, right? So next theorem. Theorem 4 or rank 4. Suppose D3 over 3 is greater or equal to D4 over 4. Then we get, let me see, I need another here. Then we get gamma 4 is equal to gamma 4 prime 1/4 over D4 minus 2. Well, that was not sufficient, unfortunately. This would fit there, but there's another coming in, 1/2 D2 minus 2. Again, we thought maybe there's a pattern. This just comes in and maybe some more come in, and then we proved theorem 5. And then we'll see that it didn't really succeed. Suppose dp, here we even need more assumptions, greater or equal to dp plus 1 over p plus 1. Here we only need this assumption here, not that d2 over 2 is greater or equal to d3 over 3. Here we need all of them, and this for all p1 lesser equal to p lesser equal to 4. Then we get gamma 5, and we even can't show the inequality here is greater or equal to, and now min gamma 5 prime, of course this comes always in, and then we have here some more, d2 minus 2, this is this one here, then also 1/5 d5 minus 2, which is this one here, but unfortunately some more coming. d1 plus 2, d2 minus 6, and then here this goes on, 1/5 d1 plus d4 minus 4, 1/5 d2 plus d3 minus 6, 1/5 3d1 plus d2 minus 8, and finally 1/5 d2 plus d3 minus 5. So we cannot show equality here, because for equality we have to show that all of these values can be attained, and for some of them we can't show this. So we don't know actually whether this equal, or maybe it's even better. So and this actually the proof of this is the longest one, although we don't have we have the worst result. Anyway, if C is general, one can improve this. Corollary C general, we get that gamma 5 is equal to the minimum, and then it gets easy, because here we know all the invariants, right? If we know all the invariants, d1, d2, I mean these are the gonality invariants, then we can compute. I mean, in the special cases we can compute the minimum, of course, right? Okay, so for here we know all the invariants, and for some other cases we also know one can compute this if one wishes, right? Minimum gamma 5 prime, 1/5, and then we have here g minus g over 6 plus 3. And here one can show that it's equality. And this number can be smaller than this. This we don't know actually, so we can't say anything, okay? Okay, these are the results in these cases where we have this inequality here. What about plane curves? For plane curves, we do not have this inequality always. In one case we don't have, but also if we know the dRs, we can compute. And this I would like to show, to give the results finally. So last case, or maybe when did I start?
50.
50 I started. Okay, then I had the time, yeah, okay. To recall the results also for plane curves. There you have complete results also. I mean, it's not important that one has this inequality for something, but that one knows the invariance. So we know that for plane curves we know the invariance, and then we can compute this. So results for plane curves. 6-section plane curves. Smooth plane curves, this means, right? Okay, so let C be a smooth plane curve of degree delta greater or equal to 5, because, degree 4, Clifford index is too small, the usual Clifford index. Then by Noether's theorem, all invariants are known. I quoted last time Noether's theorem, and I just give the theorem. So we have A, gamma 2 is equal, I mean from the theorem you see that it's different already from the other cases. It's 1, and here we have delta over 2 minus 1. If delta is equal to 5, and this is if delta is greater or equal to 6. Okay. Second, gamma 3 is equal to the minimum. Here again we have a minimum here. Gamma 3 prime, 1/3 of 3 delta plus 1 over 2 minus 2. Okay? Complete result here. Here we don't have this inequality, but we know how the invariants are, so we can prove this, and then C, gamma 4 is equal to the minimum of gamma 4 prime, and here we have delta over 2 minus 1. And secondly, here we can also compute gamma 5 is the minimum of gamma 5 prime, 2 over 5 delta minus 1. Again, because, I mean, this simplifies from the other case, because we know all the invariants and we can see what is the minimum of those invariants which we had there, right? And then we have just to show here, in general we had greater or equal here, then we have just to show that this can be attained. There is a vector bundle with gamma of E like this, and this we can do, so we have equality here, okay? Let me finish with problems. Well, the problems are the obvious ones. Right? Find better bounds for gamma 5. And bounds, we don't have any bounds for gamma n greater or equal to 6. We don't have any bounds. I mean, essentially the problem is that the lemma of Raman, Paranjapa-Raman is sort of very weak. One should find a better one, a better method to attack this problem. At the moment we don't know. And the second, of course, which is more important, find bounds for gamma n prime, which you do not know at all, at least if the Clifford index, the usual Clifford index, is greater or equal to 3. Okay, thank you.